There are a number of different shapes of bolt heads and screw heads. You might be familiar with the traditional hex head bolt. Some bolts sit up above the material. Some bolts sit flat with the material. They are flush with the material. And that is the purpose of something called a countersink. A countersink is used with a flat head screw and an oval head screw or bolt. And it makes there's a special bit, and it makes a cone-shaped hole, a conical hole that matches the shape of the flat head. And when you put the bolt or screw in the hole, it will sit flush with the top surface. It will not stick up and cause problems. The standard shape of a flathead screw is an 82-degree angle across the bolt head. There are other angles. You can also get 90-degree and 100-degree angles. When you call out your dimension for the hole, you need to match your call out with whatever angle of bolt head you're going to be using. And for most bolts and screws around here, 82 degrees is standard. Can I just point something out before we go on? Notice that it's 82 degrees from one side of the screw head to the other side of the screw head. Watch out when you're drawing one of these sloping lines. It's really 41 degrees from the center line up and another 41 degrees from the center line down, isn't it? So if you were to just start at the center line and draw an 82-degree angle, it would be way too spread out. So that's just a tip for thinking about how are you going to draw that angle. When you call out a countersunk hole, you have to do this. First, you call out the diameter of the hole. There's a hole that goes through your part, and that's what this 6.5 is an example of. They've said through, but they didn't need to do that. Then you give the countersink symbol, which is a flattened V shape, and we don't just make a letter V with our keyboard. We have to go up to the mText editor and get the special flattened V-shape thing. So anyway, diameter of the through hole, countersink symbol, diameter of the countersink, and then what angle the countersink is. So this diameter 10 is how far it is from the outside edges of that countersunk hole. Now you might say, oh, wait a minute, where is the depth of the countersink? Well, you give them the diameter of the countersink, and the depth is wherever it ends up. So you get your, let's say you're the drill press operator, you put your countersink bit in your drill press, you pull it down until it reaches a diameter of whatever's called out on the drawing, and then you stop. And you don't care what depth it is, it just cuts until it runs into this smaller hole. All right, so you can use essentially a leader line, really a diameter dimension with some stuff added to it. You can use that method to call out the countersink, or you're also allowed to dimension the whole thing with pure diameter, depth, and angle dimensions if you prefer. ASME allows either one, and you're also allowed to combine dimensions and leader line callouts. Just so you have the source material, here is the page from the ASME standard which talks about countersink holes. And here's what it says, and here are its examples showing what is correct. For example, you might be drawing a striker plate that goes on a door latch. Here's one. You're probably familiar with those. You've seen the flathead screws that go through those plates. Here is a drawing of that plate with its call-out. This is the part that we're going to draw. We're actually going to draw two parts today, one with countersinks and one with counterbores. So this is the one with the countersinks. You'll need 3 views for this part. In the top view, you'll be calling out where these holes are located, 0.45 from one edge and then 0.80 apart. You'll be pointing at the countersunk hole with a leader line or a diameter and calling out the size and the countersink details. Also in the top view, you'll see this cutout hole as a half of a circle, and you'll dimension its radius. Then in the front view, you'll need to dimension the height, the width, and the width of this top surface here. The side view may not actually need any dimensions. It might just be there to show. You can use your discretion there. Now, there's a 3D model of this part that you might find helpful for visualizing. So let's go look at that. Here is that part, and here's our 3D orbit thing. So in the front view, you can see there's generally the profile of the thing. Let's look at the top view. The top view is where you will see this cutout as an actual half a circle, and here you're seeing the countersinks. And then in the side view, look at this. The side view is the tricky part. In the side view, that circular cutout turns into an ellipse. Look at that. It's a half of an ellipse. It starts at that, I don't know what you call it, that short vertical leg. This is a half an ellipse here. So you'll want to use a method similar to what you used in your auxiliary view drawing to run construction lines over into your side view to figure out where your ellipse goes and how high it is.